Hey guys, today we're going to be answering the question, what is a linear function? Now, we're going to answer this question in three ways. We're going to talk about what does it look like as an equation, what does it look like as a graph, and what does it look like as individual points of data. You'll notice I already have a data table up here. That's just so I don't got to draw it and take up that time on video. So a linear function, in terms of a definition, is an equation that involves both an x value and a y value. And as one increases, the other one increases by what I like to call standardized amount, or at a constant rate. That's probably a better way to put it. Now, the most likely version of a linear equation that you've heard of before is actually something known as a slope-intercept form equation. Now, that's a topic for another video, but I'm going to use it to represent that. Y equals mx plus b. Now, this is a traditional representation of a linear function. We have our x term and our y term, our two variables. A lot of times we think of these as an input and an output. For example, you choose a value of x and put it into the equation. The equation does its work and it throws out a value for y, right? Now, we have these other weird variables in there, right? And again, we're not today going to be talking about exactly what those variables are, but what these variables mean is one is a constant, otherwise known as, you might think of it as kind of like a starting point, right? This is where the line kind of begins. And then the other one is a rate of change. What that tells us is every time we go up some value with x, then our rate of change tells us how much change we need in y. Now, I think this data table really clearly illustrates that point. We have our inputs here as x, and our outputs here as y. Now, to be able to identify that a set of data is linear, it means that as you have a change in the input, there should be a equivalent ratio of change in the output. Now, here's what I mean by that. How much change is there between 1 and 2 in the input? Well, there's just plus 1, right? We're just adding 1 to get between these numbers. In the same vein, as we're going between 2 and 3, we're just adding 1 again. Whenever we look at our output, our y versions, going between 12 and 15, well, that goes up 3, right? And then between the next ones, we go 15 to 18. So that tells us there was a constant amount of change between our inputs and our outputs. When we went up 1 for our x, we went up 3 for our y. When we went up another 1 for our x, we went up another 3 for the y. This is the idea behind linear, meaning that we're not just going to randomly go up by 5 this time and then maybe only go up by 2, maybe go up by 10 the next time. It's not going to do that. We are going to have an equivalent ratio of change. So let's take a look at this. How much did we increase in our input between 3 and 5? Well, in this case, we added 2, right? So how much should our output go up? Should it still just go up 3? No, because it was going up 3 whenever our input went up 1. So therefore, if our input's going up 2, it should go up twice the amount, so it should probably be going up 6. Does that happen? Yeah, between 18 and 24, we have plus 6. Now let's continue looking at that. Between 5 and 10, how much does that go up? How many numbers are in between those, right? There's 5. It's going up 5 whole numbers. So this should go up in increments of 3, 5 times. So that would be a gain of 15 it should be having. And take a look at that. Between 24 and 39, there's 15 numbers. You know, we have 15 that number increased, I should say. So this is how we can identify if individual bits of data are linear, is if we can see that for every increase we have in X, we have an equivalent or corresponding constant increase in Y. If any of these numbers were off, if this said plus 3 and then that one was plus 4, not linear, because they have to correspond to how much we're going up in X. So what these mean, that M in our linear function, that's pretty representative of this change. The fact that every time we go up 1 in X, it goes up 3 in our data set, it goes up 3 in Y. That's our rate of change. That's what we're talking about. Now the constant, or the starting point, that means what would Y be, what would our output be if we didn't put in anything for X? So if I would have had a data point that was 0 here, what do you think it would have been? Yeah, I bet you know it. It would be 9, right? That again, that's a discussion for another day too on how exactly to get those. But that would be, you know, if we had a 0 in our data set, if we didn't put in anything for X, what would our output be? What's that starting point, as I like to call it? Now, I know I mentioned we'd also talk about linear functions as a graph. What does it look like? Well, here's the deal. A linear function as a graph looks just like that. A straight line. That's what linear means, is straight. So, if you have a line that curves, not linear. If you have a line that, you know, zigzags up and down, not linear. The line has to be perfectly straight for the entire duration of it. It doesn't have to go on forever, but it just needs to be perfectly straight for that entire section that the line exists. All right. I know this is kind of a complex topic. There's a lot to unpack here. I put forth a lot of information. So if you have any questions about this, feel free to drop them in the comments below. And I'm also going to have some other videos that actually have us graph linear functions or, you know, work with linear equations. Maybe taking a look at some of those and getting some hands-on practical visualization of how this works might help as well. If you have any questions about this, feel free to let me know. I'll help out however I can. Thanks for watching, guys.